Right, okay, question 2. Does this standard thing of always giving us these definitions, doesn't it? A simple graph, one in which any two vertices directly connected by at most one arc, and one is connected directly to itself. A connected graph is one in which every vertex is joined. A simply connected one is both simple and connected. Josh has drawn a simply connected graph. Well done, Josh. It has exactly 6 vertices and exactly 8 arcs. 4 of the vertex orders are 2, 2, 4 and 5. Without doing any calculations, without drawing any graphs, how do the given vertex orders show that Josh's graph is not Eulerian, however you want to say it? Well, actually, one of the things that we know is that graphs, if they have an odd node, there must be another odd node, because they have to go in pairs, because the total of all the orders has to be an even number. So the total of all the orders at the moment would be an odd number, so we need to have another odd node in order to make it finish off doing the graph. So for part 1, part A, actually we know it can't be Eulerian because it has nodes of odd order. Not all the orders are even. So not Eulerian. That's the first bit. Part B, Josh's graph is semi-Eulerian. Well, how do we know that? We know that odd nodes occur in pairs. And there's one odd node in our list, so the other one must also be odd. So the missing node is odd. Therefore, there are exactly 2 odd nodes. And that's what we need for it to be semi-Eulerian. Okay, what were they accepting? They wanted you to say that, yeah, the missing one is odd. There's 2 missing ones, aren't there? Yeah, so one of the missing ones is odd and the other one must be even, but there would be exactly 2 odd nodes. Part 2, without drawing any examples, so again they don't want you to draw anything, calculate the values of the 2 missing vertex orders. Briefly explain your reasoning by referring to properties of the graph and their consequences on the vertex orders. Okay, so what do we get with this? That there is an important point that quite a lot of people missed in their answer to this question. So, we are told that there are 6 vertices and 8 arcs. So 8 arcs, that tells us if there are 8 arcs, then each arc contributes 2 to the total of all the orders. So the total of the orders must be 16. If we add together the numbers that we've been given, 2, 2, 4 and 5.
How do you know that the total is 16?
So every single arc in a network has 2 ends to it. And so each of those ends contributes 1 to the order. So if you add together all the orders, it's twice the number of arcs. And that's always true in any graph. And in fact that's true whether the graph is simply connected or not, because even if they loop back, it still has the same property. So what does that come to? Is that 13? So the remaining 2 arcs must have order adding up to 3. So the order sum of the 2 missing arcs is 3. Now that means they could be, well, they could be 1 of 2 things. They could be 0 and 3, or they could be 1 and 2. That's the only possibility. But the question told us that the graph was a simply connected graph. So an order of 0 isn't possible, so it must be 1 and 2. but that's not possible as the graph is connected. And if the graph is connected, there can't be a vertex of order 0. So it could be 1 and 2. So that must be 1 and 2. So the answer is 1 and 2. Does that make sense? And that was, it's a tough one because there was 1 mark there really for recognising that 0 is not a possible, not a viable solution for that. But don't forget, you know, an order of a vertex can be 0. That's something that you need to consider. In a connected graph, none of them will be 0. The last bit, argue in words, without drawing any examples, why any graph that fits these requirements has the same structure, in the sense of which vertices are directly connected to one another, as the one that Josh has drawn. So we have established, for part 3, that the one that Josh has drawn is simply connected with orders. And we've got the full list now, haven't we? So it's 1, 2, 2, 2, 4, and 5. And they are the orders of all the things. So if we think through how the graph is drawn, there are 6 nodes there. So the one of order 5 must be connected to every one of the others. Okay, and that's sorted the one of order 1. That's the only one that's connected to the order 5 one. The order 4 node is connected to all except the order 1 node. And that must be true as well, because there's no flexibility in that. The order 1 node is connected only to order 5. And I think we've worked out what's going on with the others as well, haven't we? So the 3 order 2 nodes we have connected only to the order 5 and the order 4 node. And there's no flexibility in what's happening with them. That's supposed to say 3. And we've explained that, and they're not connected to each other. That's it. That's the only way. So that's the only possible graph. There we go. That's how we just needed to explain how everything was connected. I think people found that quite hard. And somebody wrote something about how this is supposed to be maths, and so I'm not going to write something in words. Was that you, Matt?
Yeah, Boots on to.
Just as a matter of principle, you refused to answer that question. It said, answer
We'll
it.
have the same thing on his. Reading by you.
So you cheated. Right, well, yeah, were you cheating then?
Well, I scribbled it out, and it was at the end of the exam. When she was collecting.
There wasn't at the end, I was sat next to him.
Right, but you were watching what they were doing as well during the mock.
Nah, I was just like sort of moaning over and I was like, what's happening here?
We've got this all on video as well. This is just a catalogue of crime.
Oh, Dave, you're all communists. So.
And that's maths.